Hello everyone. Today we're going to continue our presentation on statistics, and we will be covering inferential statistics so that we can continue what we have built yesterday about descriptive statistics. So let's get started. Let me get the slides. Let's get started. So the whole concept about inferential statistics is that you are going from a sample to a population. So what does this mean really? So let's say you and I decide to open a coffee shop. This is a good example. And we get some coffee from Colombia or something, right? And they immediately ask us that we only sell, let's say, a ton of coffee and say, this is too much, we need to test it first. So what we do, let's say we have a class of 50 people in class, and we bring in some coffee machines, we bring in our coffee, and we want to make an assessment if the same amount of people like the coffee or not. So essentially what we are doing is we are testing, let's say called a test pilot, and testing out if this is the case. So if we can sell our coffee to the initial sample, and if the same sample, like for the same proportion, let's say 80% of people, let's say out of 50, so 40 people like the coffee, we want to assess, let's say the college campus has 20,000 people, if 20,000 people like the coffee or not, so that we can then buy more coffee because we already have a degree of certainty that the same proportion of 80% of people will like the coffee as well. So to do that, we first do our test, so bring in some machines, we have a simple survey, so it's just yes or no, no possibility of open-ended questions, so just yes or no, likes the coffee or not. And then what we do is we need to use a formula that we account for an error, and we'll get to the errors later on. But for now, just think about it. We are assessing from a sample to a population, we are introducing an error, and we want to assess what's the amount of people that we need to use to test as our sample size so that we can infer to the population, so that we can test if the population true parameter is there or not. And it comes down is around, I think it's 250 people. So essentially we conducted our pilot study. Now we're doing our official sample study. So 250 people, let's say. And let's say, just to keep this thing simple, exactly 80% of people also like the coffee as well. So now what we do is we are now going to infer to the population, this parameter, this true population parameter, that 80% of people, like out of 20,000 people, so 16,000 people like the coffee. And we introduce an error, meaning we are saying that there might be some variability because by default we're introducing an error. So this is the concept of inferring to a population. So the population is too large, we use a sample, we know we introduce an error, but then we assess if we want to keep having this conversation or not, so buying coffee and then start serving that coffee to people, okay? So this is the key difference, because essentially we started off with first collecting the data, we treated the data in EDA analysis. Now in descriptive statistics we study the data, then show it in graphs. And now it's about time to infer to the population. This is where statistics starts getting interesting. So essentially when you introduce information to people, when we are inferring from a sample to a population, there are some key things that are important to know. Let me just get this a little further away. Okay, here you go. So there's one concept that is important to know, is that us as in statistics, most likely you will find that in tests, in exams and all that, it's like they show things to you in a way that seems to be like you have to come up with the calculations on your own, out of nothing. When in reality, your job as a statistician is to choose the available tools that you have available. And this specifically comes down to distributions. And let's continue this talk with distributions. So when you have a model, let's say you have a situation where, say, you throw a coin or throw something in, you have some sort of outcome, there's already a distribution for it. There's already a tool that solves that for you. You want to assess a probability of that happening. So it's not you're not coming up with this out of nothing. This already exists. So in statistics, what we do is essentially understand exactly the problem that you have in front of you, and then you choose the specific distribution that you're going to use in order to solve your problem. Okay, so when you have tests, think about it like this. Okay, so I have a problem, I have a situation that it requires some modeling so that we can create a probability output from it. So you're not coming out of this out of thin air. Your focus is solely choosing the distribution that fits for this type of problem. Okay, so it started initially talking about the coffee, the inference. Now we're getting specifically talking about probability distributions, and later on this will be useful to us. So then we'll revisit the coffee problem again. For now, let's focus on distributions. So what are distributions? Distributions are essentially black boxes, so that we can model to, and they can show us the probability of that scenario happening and give us real numbers. So a situation like throwing a coin, throwing a dice, let's say having any situation happening, an event happening, there are already distributions for it. So this is how we essentially come up with probabilities of things, because we choose the correct distribution in order to get the correct outcome, most likely outcome from it. So essentially you have our variable like we talked before. So we have x follows a distribution, so our black box. So the distribution receives some parameters. We'll see that some distributions have more parameters than others. For the most part, they're kind of similar, but we'll go through these in more detail. And then it will provide you an output. A key important thing to know is that one event will give you a probability. Okay, keep this in mind. So we have essentially two types of distributions. We have discrete distributions and we have continuous distributions. So think about it. Yesterday we talked about like discrete stuff. So a pencil, two pencils, and so on. Two people, and so on. So discrete variables. And then we have continuous variables. That it's not about counting. It's about measuring. So the same on the same token, you have distributions for discrete variables and distributions for continuous variables. We'll get to those in a bit. These ones that I have highlighted here, for the most part, we'll start focusing more on these later on, and I'll show you why in a bit. Another key topic important to know in distributions is that distributions also have what's called subfunctions. If it's a discrete distribution, it's called a probability mass function, or PMF, and you sum all the probabilities. If it's continuous, it's probability density function. You need to integrate it because it's not about counting individually, it's about measuring. So it's within intervals. And the cumulative on this side, notice the difference between the small f and the big F. The cumulative on this side is when you have a situation where you have like less than or more than, because you are getting a bunch of the discrete ones, like individual ones, summing those all together or integrating those if it's continuous in order to have like probability of something above certain value or below certain value. I'll give you some examples. So we start off with, we know that in probabilities vary between 0 and 100% inclusive. So the key step is you choose the adequate distribution, you choose a variable to store the calculated probability, and the framework is like I explained before. So x follows the squiggly line thing, the distribution with the inputs, and gives you the probability. Okay, let's start with some ones for you to see how this works. Let's start with the binomial distribution. So what the hell does this mean? So you use the binomial distribution when you have binary outcomes, situations where it's 0, 1, yes, no type situations. Okay? Any situation that you have that involves in any way some sort of classification of its 0, 1, it's a binomial type distribution. There are variations of this, but for the most part, you're dealing with a scenario it's like 0, 1, nothing in between. Okay? And all distributions, they have properties, and mostly, for the most part, you'll be dealing with the expected value and the variance. So it's represented as E of x and V of x. For the most part, I'll be using the same letters when I can for all those distributions, because I find it's very distasteful when you find people that we're talking about the same distribution. They change the letters around, they do different stuff around. Makes no sense. This is already pretty much complicated. So might as well like simplify things at most. So what you do is what I do is I use the same letters, same consistency across the board. So it makes it easier when you're knowing what are we doing here. So N is about the number of outcomes. P is about the probability. So let's say I ask you, what is the probability of getting tails? So check at this. This is a binary event, so it's tails or heads. But it's 7 times if you flip a coin 20 times. Think about this for a minute. What is the probability? So we need the probability, so we need the probability distribution. Fair enough. Of getting tails if you flip a coin, so it's a binary event, so heads or tails, okay? You flip it 7 times if you flip a coin 20 times. So our success is 7 times, this is what we want to achieve, if we flip a coin 20 times, okay? So how does this work? Hold on. So when you use binomial distribution, you will be using, for the most part, combinatorics. And I'll get to the problem in a bit, just to show you how this works. We talked yesterday about combinatorics, where it's not statistics, but enters statistics, but it's because it's statistics math. But in itself, it's accounting. It's accounting discipline of mathematics. It's not statistics, okay? So, combinatorics, you have the number of occurrences, and you have the probability of success, which is X, and the number of events that you want. So number in total and the number of successes that you want. So we throw a coin 20 times, N, and we want 7 successes. Okay, so this is a combinatorial problem. So if we have, going back to our problem, let's say you throw a coin 6 times and we want to get the tails 4 times, so combinatorics. The formula is 6, 4, so this is the same thing. This is the same thing when you're showing combinatorics, it's the exact same thing. So 6, 4, we know the probability of getting each side is 50%. So it's just plugging in the numbers here. So N is 6, X is 4, so probability is 0.5. You just plug in the values and you get the probability. This is pretty straightforward, okay? So when you do these types of problems, for the most part, it's binomial. Now, this is where it starts getting more interesting. Most probabilities, there are all sorts of them. They have specific cases where essentially the whole thing ends when you just throw the coin or whatever it is once. In the Bernoulli distribution, so a second distribution, is the exact same thing. It's a binomial distribution, but you only throw the coin or the die once, so it ends. This is the main reason why you see the expected value and the variance as P and P times 1 minus P, because N is equal to 1. Understand? So it's a binomial distribution, but it's a specific case because it ends after one case. Okay? So you throw a coin once to get heads. So again, PMF, X equals heads, 1, 1, because it's one case only. And then it's 1, 1, so it's 50%. Okay? Now let's move on to the next distribution. The next distribution is called negative binomial distribution. So what the heck does this mean? So here it's the other way around. The number of trials is not fixed. It is the random variable. I'll explain what this means. The experiment continues until X successes. All is greater than 1 are observed. So let's say a simple example. Let's say you have, say, a salesperson that has a probability of booking people, if he keeps calling people, of 25%. So you start the other way around. You say, what's the probability that 15 people must be asked before 5 say yes? Notice how this is different now. So what is the probability of 15 people? Because we already have the probability of a success. It's 75. And now it's the other way around. It's what the probability of 15 people must be asked before 5 say yes. So the math, you just disregard the complicated nuisance from mathematics. This is no point getting into this unless you're talking about like going directly to mathematics. just focus on figuring out the type of distribution that you will be using. So 5 people, so the success is 5, 15 people, and the probability is 25. So this is the formula. So it's 15 minus 1, 5 minus 1, probability of success, the other way around, the converse one, and this is the probability. Okay. On the other way around, you have the discrete, not the discrete case, you have the one case only of the negative binomial, which is the geometric distribution. Same thing, you're calling people, 25% say yes to a meeting. What's the probability that 15 people must be yes before one says yes to a meeting? Same problem, see? The only difference is that instead of 5 people, or the number that we defined before, it's just 1, okay? So then we have 2 other cases. This one is the Poisson distribution, and the next one is the exponential distribution. These are similar, and they are connected by a factor called lambda, but it's important to understand how these work. So the Poisson distribution here, the case is number of discrete occurrences over a continuous variable. Think about it. Number of customers, so discrete, you can count the number of customers that enter a store within 60 minutes. Okay, so 60 minutes you can count, it's a continuous variable, time, and customers, it's discrete. So number of people over a continuous variable, number of accidents in a row, number of births, so number of babies, 1, 2, 3, 4, 5, and so on, at an average rate of 2, in this specific case, per hour. Okay, so then we have the other way around, which is the exponential distribution, and this is the contrary. Here is time between 2 calls, or a time an integrated circuit lasts after 10 years. It's the other way around here. And the last one that we'll be focusing for now, it's called the uniform distribution. Here, it's all values are equally likely to happen. When you throw a die, it's always the same percentage. So you, in a way, in a sense, it's a uniform distribution, because no matter which side you get, it's the same distribution. So when you look at this, graphically, it makes sense because it's a fixed value, ends up being a rectangle, which is kind of funny, because between 0 throws and let's say 40 throws, it's the same probability. Okay. And this specific one, I'm giving the example of a die, you can count each one, but the specific case of a uniform, it's a continuous distribution. This is the PDF, and this is the CDF. So for the most part, you can actually solve this graphically because you can see it. So let's say the function, it's 40 minus 0, so all the space here, and the CDF is the value that you're looking for minus the variables. So for instance, so let's say the probability of x being less or equal than 8, so x is 8. A, we know that is 0 because it starts at 0 and ends at 40, right? So you just plug in the values and you get 8 divided by 40. See what I mean? So let's say we have another one. We have x greater or equal than 30. We know that it ends at 40, so it's 40 minus 30. 40 is 40 minus 0, and we get 1/4. Okay? Let's say we have another example here. Let's say we have something x, a probability of x being between 10 and 26. So it's literally, we have a is equal to 0, b is equal to 40. So it's literally 26 minus 10 divided by 40, you have 10 fourths. 10 40s, so 1/4. Notice here that because we're dealing with a continuous distribution, when you say something like x equals 20, there's no area, it's 0, because we are dealing with a continuous case. Okay? Think about it. It's like you're dealing with a continuous flow. There is no 0. Okay? There is no probability of x being specifically equal to a specific number. And on the same token, if we ask for probability, there's outside bounds, that is not calculated as well because it doesn't exist. Okay? So let's look at now a specific example, which is a normal distribution. How does this work? A normal distribution is a special case because we have studied that what happens when you have enough data points in your data set, it starts happening something pretty interesting, which is all distributions, no matter if it's a Bernoulli or binomial, whatever the case might be, start ending up showing resemblance graphically to a normal distribution. So it might start off something like this, and then as you keep iterating more, it start looking at like a normal distribution. And the cool thing about it is that then you can use what's called a central limit theorem. And the whole point to this is that no matter the distribution that you have, as long as you have enough data points in your data set, now that distribution can be modeled over a normal distribution. So then we can use the normal distribution tables so we can figure out probabilities. It makes our life as researchers much easier. So a normal distribution, yesterday we talked about normalizing and standardizing things, but today let's get to this in a little bit more detail because this is important. A non-standardized form, so you have the mean in the specific case, so x, our variable, follows a normal distribution with a mean 150 and a variance of 50. When you normalize it, remember that we talked about getting the data set, we kind of shift it where the mean is 0 instead of 8, like our investment funds yesterday. So now when we are standardizing this, the mean is now 0. And the variance, remember, it's standard deviations. No, it's now in standard deviations, so 1. So mean here, and 1 standard deviation, 2 standard deviations, and so on. Remember that we haven't changed the distribution, we just normalized it, so we applied mathematics to it. It's still the same distribution, we just have a version of it that we can use in order to use statistical techniques. Okay? And then there are some more continuous distributions, the T and F and the chi-squared. And all these are used in what's called hypothesis testing and confidence intervals. So let's get to this in a bit. So I explained the central limit theorem. So we see that we have lots of data points and now starts resembling to a normal distribution. We have a specific case here, which is the t-student distribution. And this was a mathematician that discovered that under some assumptions, when you know variance, when you don't know the variance, when you have a smaller sample size, there's an adjustment that you make to the normal distribution or a z distribution when it's adjusted, and it's called the t distribution. It's close to it, is similar, but it's more precise than it. And the table, I created a table here for you to use when you are, sometimes in tests they ask you which one is it. The rule set is this one. If it's a known distribution with a known variance and the sample size is less than 30, you use the z. When it's greater or equal than 30, use the z as well. Same thing here. Known distribution, unknown variance, use the t version. Okay? This is the same thing. So unknown distribution, known variance, unknown distribution, unknown variance. So it's this one, you don't have cases for this one, but for these ones you have z and t. Okay? So how does this work? Notice we talked about the chi-square distribution, and this is an important one because this is a normal distribution squared. I'm going through this kind of an overview, and we'll get to more exercises later on. It's just to show you that for the most part, these distributions are kind of modeled after some cases, and then it's kind of specific cases of the main distributions. And the chi-square distribution, that's literally the normal distribution squared. And I have a proof here for you, because if you take the values of the z-score values, when you get a significance level of 95, the corresponding values, when it's a two-tailed test, it's between minus 1.96 and 1.96, so you get 95. But if you take the chi-square distribution with the same value squared, the 3.8416, you get 95 as well. Okay? It's just to show you that all the distributions that we saw earlier on, get you this before. I had the table before, just to show you that here. So for the most part, these are kind of variants of the same concept, just to show you that it's more about the specific case that you have that you want to ascertain the best tool to use, and just know tools that you start getting more comfortable with these tools because you're doing more exercises. But for the most part, they're very related. It's about you choosing the tool and then do your exercises. Okay. Now, for the chi-square distribution, we also have a specific case. We have the goodness of fit. So we have two ones. We have a goodness of fit and the chi-square test for independence. chi-square goodness of it tests the measures of discrepancy between the expected value and the observed value. And I'll show you this in a bit in linear regression. And the chi-square test for independence, it's the same thing as above, but with two variables. So one is for one variable, so observed value, expected value, and the other one is the same thing for two variables. Okay. So we have some math here. Now I'm going to show you, in statistics, for the most part, you'll be using tables, especially when you are in academia, and you want to know exactly what's the point of this. So why do we use tables anyway? So let's say we have a binomial table. We have a binomial distribution, and we have as parameters t and 45. And we are asked what's the probability of x being less or equal than 4. Because this is a discrete distribution, this means that because it's less or equal than 4, you need to sum all the events until that point. So 0, 1, 2, 3, and 4. So you'll be needing to do the math all these times. So it's 0, 1, 2, 3, 4. You actually need to do this 5 times, really. So there's no point to this, because if I ask you what's the probability of x being less than 45, it would be a horrible one, because you need to do all the calculations. So this is where we use tables. Notice here that I have in the binomial distribution table, I'll get this here a little larger for you to see. This is a binomial distribution table, and when the probability is 0.45, and when we have x equals 4, when n equals 10, which is our case, so the parameter is 10, the probability is 45%, right? And we want to know probability of x being less or equal than 4. Notice here how the calculation is already done. It's 50.44, the exact same number that I calculated here for you. This is the power of tables, because the calculation is already done. Obviously, now we do Python, we have all sorts of calculation tools like SPSS and Stata and so on. This is just to show you that earlier on, people didn't have this. So they created tables where they went through all this trouble to calculating all the stuff, so that it made it easier when they had the problem, so that they could immediately get the value directly. Okay. So in continuing to the distribution tables, it's important to also understand this from the point of what's the cumulative distribution function, and this is where the tables come in, because we are calculating cumulative distributions. Earlier we talked about like individual probabilities, and tables, the whole point of this is that you are calculating cumulative distributions. So this event, I have the graph here for you, the probability of x being less or equal than 4, so it's 0, 1, 2, 3, 4 inclusive, and then you have the probability. Okay. So in summary, when you're talking about statistics, we talked about the discrete case and the continuous case. So essentially we have two sub-functions. We have the PMF, we have the PDF. And when you do the CDF, meaning the cumulative distribution function, when it's the discrete case, you have what's called a step function. Okay. When it's the continuous case, which for the most part this is what we'll be using when you're dealing with continuous variables, it's a sigmoid function, and later on we'll talk about logit and prove it, and it comes from this. It doesn't mean that you can't use continuous data to do a classification problem. It's just the cumulative distribution functions from the probability mass function or for the probability density function are different, because you're dealing with continuous variables or discrete variables. Okay. Some properties that are important to know when you're dealing with z-tables is that you need to know this one, and you can like write those down when you're going to a test, because this will be useful, because sometimes you need to do some sorts of transformation so you don't get the wrong values. So when z is greater than minus x, it's the same thing as going to get the value directly. Okay, no point getting into the mathematics of this, just memorize this or make a point, because I have terrible rote memory, so I need to make notes. So just make note of this and use it, because this will serve you later on when you're doing these types of problems. For instance, let's say you have something like this. You have z less than minus x, so now you need to shift it, so it's greater than x, so it's equal to 1 minus the cumulative distribution function. And this one is a kind of a compendium of both. So you have greater than or less than, so just plug in these ones, one minus the previous one, and you get the value, okay? So notice here, so let's say you have a probability of x being greater or equal than 3. So you know that is equal to the 1 minus probability of x being less or equal than 2. Or it's the same thing of saying 1 minus probability of x being less than 2, equal than 1, and equal than 0. Okay? Now, some key important things to know, and I mentioned this before yesterday, but it's important. Notice that we are doing calculations with the population or from the sample, and sometimes in exams they don't tell you which one is it, so you need to know. Because if they show you this, and if they show you that x bar, it's the sample. So you need to subdivide the variance, which in this case is usually represented as the standard deviation squared, divided by n. Okay, so in a specific case, let's say you have x, notice it's not x bar, it's x. X follows a normal distribution with 750 as mean and 500 as variance. They're asking you what the probability of x being greater than 700. So you normalize it, so we can use the tables. Notice how we change from n to z. So it's the probability of z being greater than x. Okay. So z being greater than, you subtract the mean and divide by the variance. Okay. And now you can say that this one follows a normal distribution 0, 1. Okay. And now we need to use our properties that I shown you before. Z is greater than minus x, remember? So it's the same thing as saying that probability of z is less than the same value, because it's the table is symmetric. Now you just plug in the value in the table and you get the value, you get the probability. Okay? So this is the way for us to calculate probabilities, and we start using tables. Now, coming back to our coffee example, when we are going to present results in statistics, it's not a point estimate for the most part. For the most cases, because you are making an estimate, it's within an interval. So you're saying, like, coming back to our coffee, that the true population parameter, like 80% of people liked our coffee, is within a certain interval. Okay. So essentially, what we are saying is that most likely, that's what we are saying, the probability of people that like our coffee, you're not saying that exactly 8%. It could be 79, it could be 81%. So it's in an interval. So what we do in statistics is use two things, really, when presenting results and when making decisions. It's about hypothesis testing and confidence intervals. What does this mean? You are making a hypothesis saying that our null hypothesis, this is how we usually present things, it's null hypothesis versus the alternative hypothesis. We are saying essentially that our main hypothesis is that our true population parameter, meaning our proportion of people that like the coffee, is 80%. Or an alternative, so our H1, people do not like coffee in the same proportion. This is how we present the initial case. So before we make our purchase of coffee in Colombia, we are asking before, is the same people like the coffee or not? So we have a proportion. And when we present results, it's not a point estimate. We present results in a confidence interval. We say that, and the simplest example for us to understand this is saying, let's say we have 100 samples that we take from the population. If we have a 95% confidence interval, which is a horrible name because it has nothing to do with confidence, it's about the error rate. If we have 100 samples that we take from the population, it means that 5 of them do not include the true population parameter. This is what this means. And later on we talk about type 1 errors and type 2 errors. Just want to understand for now that when we are making an hypothesis, we are entering with a concept also with an error. And we are essentially saying that we are testing out if the true population parameter, meaning the population, like 80% of them like the coffee, but we also adding an error, meaning that if we gather 100 samples from the population, 5 of them might not include the true population parameter. And we rejected that the true population parameter is in fact 80% and people in fact like the coffee, would be wrong. We're making an error. And later on we're talking about probability of type 1 errors. We'll get to this in a bit. So the key point is, when talking about hypothesis testing, you define what we are hypothesizing. We extract the sample from the population, so we did that with a coffee example. We find out the parameters we know from the population, so we can choose the right distribution. In our specific case, because we have a sample size above than 50, it's 250 people, like we saw yesterday, so we can use the normal distribution. So we conduct a test, we then normalize the distribution, and we calculate the test statistics. So let me show you how this works. So let's say in a simple example, let's look at this table. Notice here that we have this situation. We have an hypothesis test that we are doing, and we are saying that with a 95% confidence, if the true population parameter, meaning 80%, is within our null hypothesis, so this white region. And the grayed out regions are the alternative hypothesis, meaning that the true population parameter is not there. So when we define a 5% error rate or 95% confidence interval, essentially what we are doing, we are defining a critical value, a bound, from which if the calculation that we get from the table that we saw earlier on, if that does not lie within the specific region, we reject the null hypothesis. Or, if it's the other case, if it's actually within the region, we accept it. And for this, we have some math to show you this. And if people have less experience with this, just bear with me for a minute, because when you're using the tables, if it's a two-tailed test, meaning this one, this is where we are, so 90, 95, or 99%. These are the z-scores, or the standard deviations, it's the same thing, from the table, from which we'll be serving you as a critical bound, separating from the null to the critical region. Or when it's a one-tailed test, it's the same thing, but it's either this one or this one. Notice how the values are the same after a specific value, because in reality what we are saying is that if you have a 5% confidence interval, we are splitting this in two parts. It's 2.5% for each side. So a 5% confidence interval, it's here, and we have a 95% region here. Same thing for this one. But for this case, it's 5% divided by 2, so it's 2.5 and 2.5. This is the difference. This is the thing, because you see the difference here. Okay. So again, if you have a test statistic that lies within the critical region and the separation, let's say, is 1.65, you reject the null hypothesis because the test statistic that you found is here. Okay. It's the same thing here. So if you have a normal distribution here and you have the value that is here, and this is the critical bound, so you reject the null hypothesis. Okay. So now let's talk about the error. So what does this mean? The error rate that we talked about before, it's about the probability of you rejecting a true null hypothesis. That's the significance level, or the p-value, or a type 1 error. It's the same thing. And the contrary of it is a correct decision, meaning you accept a true null hypothesis. Okay? And the other version is when you accept a false null hypothesis, meaning you reject a null and accept the alternative, and you would be wrong. So this is a type 2 error. Okay? So I'll give you some examples later. So let's look at this example. So let's say you have an observation taken from a geometric distribution. So they're telling you that this is the distribution. So we talked about this here before. So this is the distribution here, and 0 otherwise. And they're telling you specifically to test if the probability of it's 0.4, and then the alternative hypothesis is greater than 0.4. So you are in this situation. Let me show you here. You have a one-tailed test. Okay, this is what this means. And they're asking you here, what's the probability that a type 2 error, meaning you accept a false null hypothesis, will be committed when the true parameter value is 0.6? Okay, so how do we solve this? So type 2 error, so we know that it's accepting a false null hypothesis or rejecting a true null hypothesis, same thing. So the type 2 error, knowing that the probability is 0.6, so you just plug in the math, and this is the probability. Same thing for a probability of type 1 error, and you get the calculated probabilities here. For now, we can do calculations later on. I just want to show you for now just the overall view. We'll later on do more calculations. For the most part, just forget about the calculations for now, just to understand that in statistics we can model, use the distributions, calculating errors, calculating probability of type 1 errors or type 2 errors, and we can then assess where we are in regards to our hypothesis, our testing. Okay, just for now, let's leave this at that. It's more important to understand the concepts than getting into like more details about this. All right, so we can test all sorts of things in statistics, like we can test variances, we can test sample means, and so on. And I want to show you just for now the key concept about the estimators. So when we calculate a probability, we can then infer to the population. So we talked about getting a hypothesis test. We define if the thing is true or not, if it's that specific case, and we present the results within a confidence interval, saying that the true population parameter is 80% plus or minus something. Then we enter a specific case in statistics, which is the estimators. What does this mean? The estimator is the formula or the best formula that can get you from the sample to the population. So it's not about an estimate, which is which you calculate with an estimator. This is about what the formula that you use, the best one to get from the sample to the population. So how does this work? So let's think about throwing the dart to the board, right? The estimator, it's like the formula that tells the robotic arm how you can throw things. So like a specific angle, a specific strength, and a specific way of throwing things with an angle, and so on. That would be the formula that would be as an input to the computer, so that it can get to the access on what the formula is telling it to do, so that it can throw the dart. Earlier on, when we talked about the confidence intervals and the hypothesis testing, this is the best way for us to see this. The estimator, notice the hat, we want to get to the true population estimator, right? So we want to get from this one to the true population parameter. So the expected value of the parameter from the sample, right? We want to get to the population parameter, and we are adding an error. And our results will be within a confidence interval. This is the best way for us to look at this, okay? So now the question is, how do we compare estimators? So what's the difference? We usually in statistics, we talk about the bias variance trade-off, and this is a key important concept in statistics, and understandably, because we want to be as most accurate as possible, but we do not want to be biased. So what does this mean? Let's say you have a situation where you go to, let's say, a colleague of yours, and everything that you tell them, they say yes. No matter what you tell them, they say yes. So they have a high variance, and will be overfitting. Because if you take the same things that you're asking that person and take to another person that doesn't know you, and it's a little bit more focused, probably you'll get what you see here, which is underfitting. So no matter what you tell them, they're going to say no, right? So high variance means that your model is adjusting to every single point, and it doesn't work because it doesn't generalize when you have a different data set. Right? You're trying to figure out a formula for the estimator that can work in any type of situation for these types of data sets. But if you over-test it with the same data set, it will produce a formula that just adjusts to that specific data set. Whereas if you do a different scenario where the estimator is completely, like, it does not care about the data set, it keeps doing the same thing, it will underfit because it won't serve any of those. So both cases, you don't want those. You want a balance between variance and bias. So when you look at this here in the darts, bias means centered to a specific point. That's what that means. So you want it centered, so low bias. High bias means it's not centered. It's it's not in the center that you want. And variance, it's about the spreadness of the data. We talked about the investment funds earlier yesterday, and it's about that. You could be centered, but the data is very dispersed. So you want kind of a balance between both, kind of centered and like low variance. So you want low variance and low bias. So you want this would be your ideal situation, but for the most part you'll have some bias and it will not be completely centered. But this is the key point about bias variance trade-off. Okay? So when we're talking about linear regression, we're talking about estimators, specifically machine learning. This is the key concept. You have a data set and you're trying to fit a line that explains the data set. And we already saw that it needs to generalize. I have 2 slides here. Notice that it could be like a little upper, a little down. You don't know like visually which one is better, but this is the key point. You have like a data set and you have a model that you give all these features and the model, and you tell some labels when you're training the model, so that when you provide it a test set, meaning that it hasn't seen before, it's an unseen test set, now it can fit the model that it trained with a training set so that it can fit it perfectly, or at best it can, so most centered and less variance possible, so that it can make assessments on a model. I'll give you some examples. In the next lectures, I can show you a hamburger classification model that I created, where essentially the model classifies if a picture has a burger or not. That's the key point. So all pictures, it doesn't say like from the training set that all the pictures have burgers or not. It failed on some, but it serves as a point as well, because when I tested with a different test sets with different set of pictures, it makes some wrong conclusions on some of them, but for the most part is right. So the model works because it was trained in an unbiased way, meaning it has the ability to generalize to information because it's just not focused on those specific pictures. It's like you saying, giving all the results to like a student. He's not studying at all, just literally copying the results. But if you give him like the same type of materials, but you don't give him the answers, he doesn't know. This is the key point. So he needs to have generalized information about the types of answers that he can deliver, so that when he sees questions that he hasn't seen before, he can answer those. This is the key point to machine learning. Okay, so we talked about distributions, we talked about chi-square distributions and goodness of fit, and this is the key point. It's the difference between the observed value and the expected value. The expected values are all the values that you have on the line, so your model, you expect it to perform in a certain way, and these are the observed values. Okay, so we have all sorts of techniques to estimate, essentially estimated techniques. We have a bunch of them. The first one is called OLS. The second one is MLS, and the third one is MME. Let's go look at through these in more detail. So we saw that an estimator needs to be unbiased, efficient, and consistent. We saw about the errors. Now let's talk about the OLS. So the OLS, essentially, it's a linear regression model, but the key difference really between like the typical minimum squares estimation is that it has more angles. It has more, it can be, it's not necessarily a straight line, it could be something like this, like a polynomial line. That's the key difference. So essentially you have different labels, you have different equations. X follows a normal distribution, 0, 1, and then there's math that you can go through this, and then you calculate the line. That's the whole point of this. Step 1, this is how you do it. So you get the errors, the summation of the errors. You get all the values inside. Then you find the derivative of the sums in terms of alpha n equal to 0, and do the same thing for beta as well. So then substitute each term and you get the expected values. The maximum likelihood estimator, and again, this is the whole point of this, is not doing like a bunch of math today, just to show you like the key concepts so that later on we can work on the problems. So this next one, maximum likelihood estimator, this is one of the most powerful ones, and for the most part, especially in econometrics, we'll use this a lot. This is the key point. So when we fit a line, now the concept is we are using a Gaussian curve. And a Gaussian curve has a specific characteristic, which is the derivative of this when it's equal to 0, and the maximum, you are at this point. So what this means is that if the bulk of the information lies within this bound, if we calculate the maximum and we get an asymptote, and that's, think about like this, rotating this. I'll show you this, how this works. So the maximum is here, where its derivative is 0, and the bulk of the points are here. So if you think of the line, when you're trying to estimate the linear regression line, and you kind of like shift the Gaussian curve, like getting on its feet, the asymptotes and the maximums, all the maximums get you the line. This is more powerful because essentially we are saying like a bunch of points, like the 68% of it, the bulk of it, are lying there. Lying, not lying as in lying, lying as in staying there. So the maximum gives you, for each one, for each group of points, gives you the maximum, and from which you can get the line. The way for us to calculate this, because in statistics we talk about independently identically distributed data set. What that means is that each points you can multiply those because those are independent. That's what that means. So when you have a maximum likelihood function, you use the product function. So you have a distribution function here. This is mathematics to get the terms out. We'll later on, don't worry about the mathematics of this, just think about this for a minute. So we have the sum function, so you sum stuff. You have a product function where you multiply stuff, okay? So you have the function. These are simplifications where you can take terms out and multiply the product function, simplify it. So this is the first step. We'll get to more problems later on. For now, don't worry about this. Then you do the logarithm to it, to the result that you got. You equal it, you differentiate it and equal it to 0. And you will get an estimator. So your parameter, when you calculate it, essentially it's telling you that this is the estimator. A maximum likelihood estimator is using sufficient statistics. So it's using all the kind of optimized values to give you the optimal estimator, from which you can calculate the true population parameter. Okay? And the last one that we will address today is what's called the method of moments. The method of moments is an interesting concept, which essentially is you have a way of relationship between the sample and the population, and each one is a moment. So the first one, notice that it's power 1 and all the way to power of n, m1, m2, m3, m4, and so on. And you have the same thing seen from the sample side. Okay? So the key point is that you can find the variance, you can find the expected value and skewness and so on, just using the moments. Notice, contrary to what you see in textbooks, this is not the mean, the first one. This is not the mean, and the second one is not the variance. It's a moment. And from those ones, you can calculate the mean and the variance. And to do that, we use what's called a moment generating function. I'll get this a little larger for you. Let's see if you see this like this. Good. So, by definition, a method of moments estimator, this is the formula. It's the expected value of use of function e raised to the xt. And at t equals 0, then when you have m where it's equal to 0, it's equal to 1. So what does this mean? If you're using this discrete distribution, this is the formula that you use. Remember, use summation when it's discrete. And when it's continuous, when it's a PDF, you use intervals from 0 to plus infinity. So let's look at some examples. So we talked about this before. Let's look at some examples. Before that, just a key note, remember that variance, it's expected value of x squared minus the mean squared. And this is where the people usually refer to the first moment as being the expected value. It's not the expected value, it happens to be because it's the first moment. And you calculate it because you know that the variance is this. So, because the second moment is this value squared, you can then say that the variance is m2, because it's this value squared, minus the first moment squared. That's how you can calculate the variance and how you can get the mean. So let's look at an example with a Bernoulli distribution. So we know this is a situation as a binomial distribution, but it ends after one throw. So you have the probability of x minus the reverse, 0 otherwise. So how do we get to how do we use the moment generating function to calculate the expected value and the variance? So we start with the function, same as before, and it's because it's discrete, we use a summation. So it's you take the probability, That's all we have here. And just plug in the ETX, which what we have here from the moment generating function. Okay, and then we substitute for 0 and 1. So we do that in the distribution. So plug in the values at 0 plus the second one with 1. Because remember that the Bernoulli distribution is a binomial case. It's 0, 1. And it ends after one trial. So we get this, which is our moment generating function. So what the hell does this mean? From this, now we can find the mean and expected value. And we do that because the first derivative of the moment generating function, we will get p times e raised to t, and with the first derivative, when we plug in 0, we get p. Okay, and the second moment is the same thing, so we do the second derivative to this again, plug in 0, and we get p. So this means that the variance, because it's the second moment minus the first moment squared, so we plug in the values and see how we get the exact same variance as when we saw this before, using the moment generating function. So it's the same thing. So plug in the moment generating function, because it's discrete, it's a summation. So you plug in with a summation version. You know that when you calculate the values, the first derivative and the second derivative of it, you plug in 0 to it and you get the values. And then you can calculate the variance, because you know that it's the second moment minus the first moment squared, and then you get the values. Same thing if we did the exponential version. So same thing, this is the exponential, the PDF branch. So we have the function that we plug in here. To get the function, same thing, so plug in our member here. First derivative, second derivative, 0, 0, and you get the values. Okay, same thing. So to get the variance, you know that it is the second moment minus the first moment squared. So plug in the values and you get the numbers. So let me get this here. So this is a brief introduction to inferential statistics. We talked about the coffee example, we talked about confidence intervals, we talked about hypothesis testing, we talked about sample statistics and true population parameters, and techniques to get us from one place to the other. I hope you enjoy this content. If you have any further questions, let me know, and we'll keep doing more of these. Take care.